Okay, let's start today's lecture. All right, so last time we saw a prototype example of the transportation problem, the P and T company distribution problem, and we found the constraint coefficient of it has a special structure, which is shown like this. However, to describe the general model of the transportation problem, we need to use terms that are considerably less specific than those for the components of the prototype example. So, in today's lecture, I want to develop a formal formulation for transportation problem. In particular, the general transportation problem is concerned with distributing any commodity from any group of supply center to sources, to any group of receiving contents, client called destinations, in such a way as to minimize the total distribution cost. In general, source I has a supply of SI units to distribute to the destinations, and destination J has a demand for DJ to be received from sources. The cost assumption. We assume that the cost distribution units from source I to destination J is directly proportional to the number distributed, where Cij denotes the cost per unit distributed. Now, the only data needed for a transportation problem model are the suppliers, demands, and unit costs. These are the parameters of the model. All these parameters can be summarized conveniently in a single parameter table as shown in this table. Therefore, formulating a problem as a transportation problem only requires filling out a parameter table in this format of this table. In the middle are the per unit cost Cij, and the left are the sources. The up are the destination, and the right are the supply or the output of the factory, and the bottom, D1 to Dn, are the demands. For a transportation problem, let's first focus on a balanced transportation problem, which has the assumption of sigma Si equals sigma Dj. The left of the equation means the entire supply must be distributed to the destination, and the right means the entire demand must be received from sources. Thus, the equation presents a balance between the total supply and the total demand, which is an additional constraint for balanced transportation model. For the P&G company distribution problem, the supplier sum is 300 truckloads, and so do the demands is also 300 truckloads. So it is a balanced transportation problem. This and this, sum them O equals 300 is a balanced transportation problem. Okay, now let's talk about the unbalanced transportation problem. First, one case is the sum of supply is more than the sum of demands. There is an excess supply capacity. For the model of this case, we always introduce a dummy destination to receive the unused supply capacity. Here, I'd like to use an example to illustrate the procedure. The Northern Airplane Company. The company builds commercial airplanes for various airline companies around the world. The last stage in production process is to produce the jet engines and then install them in the completed airplane frame. The company has been working on some contracts to deliver considerable number of airplanes in the near future, and the production of the jet engines for these planes must now schedule for the next 4 months. Okay. To meet the contract date for delivery, the company must supply engines for installation in the quality in the second column. Yes, this column. Okay. The monthly difference in the maximized number that can be produced and the unit cost, each of the given in the third and fourth columns. Because of the variation in production costs, it may well be worthwhile produce some of engines in a month or more before they are scheduled for installation, and this possibility is being considered. The drawback is that such engines must be stored until the scheduled installation at a storage cost of 15,000 per month for each engine, as shown in the rightmost this claim. The production manager wants a schedule developed for the number of engines to be produced in each of the 4 months, that the total of the production and storage costs will be minimized. It's also the objective is also to minimize the cost. Okay, because the units being distributed are jet engines, each of which is to be scheduled for production in a particular month and then installed in a particular month. So we assume source I means production of jet engine in month I. The destination J means installation of jet engines at Mount J. The DJ means number of scheduled installations in Mount J. Then we assume Xij means number of agents produced in month I for installation in month J, and the Cij is the cost associated with each unit of Xj. Since it is impossible to produce engines in 1 month for installation in the early months, Xij must be 0 if I is more than J. Thus, we assign a large number to denote the list. Thus, we assign a very large number denoted by M to the unjustified cost entries to focus the corresponding value of Xij to be 0 in the final solution. Here, we can see that here I is 2 and J is 1. So Xij equals 0, and we arrange the cost to be a very larger letter M. The supply sum to, you can see the total supply is 100 and the total demands is 70. We can see that the supply is more than the demands. So we give the constraints. The constraints exist in the form of upper bound on the amount that can supplied, namely like this. We found that the only change for the standard model for the transportation problem is that these constraints are in the form of inequality instead of the equations. Okay, to convert these inequalities to equations in order to fit the transportation problem model, the slack variables are allocation to a single jumping destination and represented the unused production capacity in the respective months. Here, we add a dummy destination. It represents the unused production capacity in respective months. For the total supply is 100 and demand is 70. So the demand for the dummy destination is total unused capacity. Then it can calculate as this. So here the demand of the dummy destination is 30. With this demand include the sum of the supplies now equals the sum of the demands. This 70 plus 30 equals 100. Now the cost. We need to fill this price. The cost entries associated with the dummy destination should be 0 because there is no cost incurred by the fractional allocation. Okay, now let's start case 2, for which the total supply is smaller than the total demands. Similarly, I'd like to use an example to illustrate the procedure. Distribution of water resources. A major water district is an agency that administers water distribution in a large geographic region. The region is very arid, so the district must purchase and bring in water from outside the region. The sources of this imported water are three levels: clonable, cyclone, and kilos, the three levels. And the district then resells the water to four cities: the city of Bantu, Los Davis, Sangul, and Holy Glass. The variable cost per acre foot of water for each combination of river and city is given in this table. Like this. The median is the cost. I want to explain this line. It means that Colonial River can't allocate water to Holy Glass. Okay, now management wishes to allocate all the available water from these rivers to the four cities in such a way as to at least meet the minimal needed. It means the essential needed. So the objective, we must at least meet the essential needs of each city. Each city has, except Sangul. The manager should consider that the essential needs must be met of each city, will minimize the total cost to the district. This is an unbalanced transportation, as we can calculate that the total supply with some 50, 50, 60 is equals 106. And the minimum needed is 110. The maximum demand is unlimited because here we have unlimited, infinite. So the maximized demand is unlimited. According to the current output, Holy Glass, however, the supply is 160. So Holy Glass has an upper bound of 60. It equals 160 minus 30 plus 70. So it equals 60. Thus, the matrix demand is 210 million acre-feet, which is greater than the supply. The situation is analog to the North Airplane Corporation's production schedule problem. Well, there were excess supply capacity. Now there is excess demand capacity. Consequently, the adjustment needed here is to introduce a dummy source. To send the unused demand capacity. The imagined supply quantity for this dummy source would be the amount by which the sum of demands exceeded the sum of supply. So we use 210 to minus 130 will equals 50. So that's the supply of the dummy supplier. The cost. Now we need to enter the cost of the dummy source. The cost entry in the dummy law is 0. Are 0 because there is no cost incurred by the fictional allocation from the dummy sources. A huge unit cost of M is assigned to the Colonial River to Holy Glass. The reason is Colonial River water cannot be used to supply Holy Glass, and assigning cost M will prevent any such allocation. For a city has 2 demands. For example, the Bandung, it has 2 demands. How to solve this problem? We adjust the parameter table by splitting it into 2 destinations. This destination has 2 demands, and we split it into Bandung 1 and Bandung 2. And the demand here is 30 for the minimal needs, and 50 minus 30 to 20 is the extra Bandung's demand. The minimal needs cannot be the cost. For the minimal needs cannot be supplied by the dummy sources, so that a unit cost of M is assigned to prevent the dummy source from contributing to more than 20 to Bandung's total demand. The other 20 can meet or not meet. A unit cost of 0 from dummy source means it can be supplied by the dummy source. Now we converted the excise demand capacity case into a balanced transportation problem. We can see now we summarize the characteristic of the transportation model as follows. First one, a product is transported from a number of sources to number of destinations at minimal possible cost. The second, each source is able to supply a fixed number of units of the product, and each destination has a fixed demand for the product. The third, the linear programming model has constraints for supply at each source and demand at each destination. Next, all constraints are equality in a balanced transportation model where supply equals demand. Constraints contain equality in unbalanced model where supply does not equal demands. So this is an unbalanced model. That's all for today. Thank you.